The next algorithm that we are going to build is called the Sieve of Eratosthenes. The purpose of this algorithm will be to find all of the prime numbers up to a given number. So, as an example, if we enter the number 20 into our Sieve of Eratosthenes algorithm, we should get an array returned that contains the numbers 2, 3, 5, 7, 11, 13, 17, and 19, because those are all the prime numbers from 0 to 20. Now, there are multiple ways of achieving this functionality, and some are better than others. And as we learned in our memoized Fibonacci algorithm, optimizing the runtime of your algorithms can be crucial to your program performing efficiently. And the Sieve of Eratosthenes is one of the most performant ways of achieving this functionality. The way that the Sieve of Eratosthenes works is we start with a list of numbers from 0 to n. Let's take 20 as an example. In this case, we would start with an array of numbers from 0 to 20, like this. And initially, we are going to mark them all as prime to begin with. So how will we mark all of these numbers as prime? Well, we are going to change up our setup a little bit. Instead of our array being filled with all of our numbers, we are going to use the indexes of the array as the given number, and we are going to make every element of the array the value true. So this is what it looks like. We have a 21 element array, so naturally the indexes of the array go from 0 to 20. Then, at every single element, we have the value true. This signifies that every single element in the array is prime. Great, so that is how we start. Then we will go through our array and mark every number that is not actually prime as false. So, how will we do that? This is where the main functionality of our Sieve of Eratosthenes algorithm comes into play. First, we are going to mark 0 and 1 as false, because we know that they are both not prime numbers. Then we are going to loop through the rest of our list. On every number we hit, we are going to mark all of its multiples as false, because we know that any multiple of a number cannot be prime. So, for example, we will start at 2, and we will mark all of 2's multiples as false. So we will mark 4 as false, 6 as false, 8 as false, 10 as false, and 12, 14, 16, 18, and 20 all as false. Then we will move on to 3, and we will mark all of its multiples as false. So we will mark 6 as false again, 9 as false, 12 as false again, 15 as false, and 18 as false. Then we move on to 4, and so on. We go through every number in our list and mark all of its multiples as false to signify that they are not prime. Easy as that. There is one optimization that we can make though. Instead of looping through all of the numbers in our array and marking their multiples as false, we can stop looping through at the square root of n, or in this case, the square root of 20, which is about 4.4. We can stop our loop at the square root of n because all non-prime numbers after the square root of n will be marked as false by the time we get to the square root of n. So there is no point in continuing our loop. So overall, we basically loop through our list of numbers, stopping at the square root of n. As we loop through, we mark the multiples of each number that we pass as false, signifying that they are not prime numbers. At this point, all of our prime numbers will be marked as true. So we simply return all of those numbers in an array, and we have our answer. I encourage you to give this algorithm a shot before moving on to the next video, where we will build out a solution for it together. Good luck, and see you in the next video.